Hi, in this video we'll go over modeling with UML. More specifically, we'll look at class diagrams of UML. UML stands for Unified Modeling Language, and it's basically a non-proprietary standard, a graphical notation to create software models, and there's different types of diagrams in there, and in this video we'll focus on class diagrams. Basically, class diagrams represent the structure of the system. So it's a static, the static behavior of the system in terms of the structure, the different objects that are in the system, and how those objects interact with each other, and what their attributes are. That's the focus of class diagrams. So typically these diagrams are used during requirements analysis phase of software development in the life cycle, and it's used to model the application domain concepts. So basically the idea here is to create a high level design of the system by thinking of the high level objects in the application domain. It can also be used during system design to model subsystems, as well as during object design, wherein detailed behavior is specified. So this is the detailed design phase of software development. So it can be used during all of these three different phases: requirements analysis, the system design, and object design. It's just that the focus is different. At the requirements analysis phase, we're just trying to model the application domain concepts, whereas once we get to the object design, now we're trying to model more detailed behavior and all of the attributes of the classes and the different operations of the classes. So that's how class diagrams are used. So here's an example of a simple class diagram. There is a tariff schedule class on the left hand side, and then a trip class on the right hand side. As you can see, so this is again standard UML notation, which is graph based, where there's nodes and edges. The nodes are entities, and in the case of a class diagram, these nodes are nothing but our classes, and then the edges between the classes denote the association or the relationship between the classes. So the classes are represented using this as a rectangle. So in this case, tariff schedule is the name of the class in this first one. So here that's the class name. The second part is the attributes, and then the third part is the operations. In a similar manner, on this right hand side, trip is the class name, and then the second part has the attributes, and then there's no operations. So that's to show you quickly how a class diagram looks, and there could be a lot more classes than that. That's just a simple example. So a class basically represents a concept, any concept in the software system, and that has some attributes and certain behavior. So basically the purpose of the class is to describe all of these similar objects that have the same attributes and the same kind of behavior. So really that's the purpose of a class, and an example is tariff schedule. That's a class to hold all kinds of tariff schedule objects which have the same kind of attributes and behavior. Now each attribute has a type, a data type, to indicate what kind of data it stores, and then each operation has a signature. So by signature, what I mean is it's the name of the operation along with what are the inputs that this operation needs, and then what is the output that the operation produces, and their data types. So having said that, the class name is the only mandatory information in the class diagram. The attributes and the operations are optional. So typically you'll see that in a high level design phase, we identify mainly the classes and the relationship between the classes, but then once we get into the detailed design, that's when we begin to identify the attributes and the operations. So here the notation is shown. So like I said, the first part is the class name, the second part is the attributes, and then the third part lists all of the operations for that class, or the behavior for that class. Now in addition to this, now the type specifying the type is optional, but then it's always a good idea to specify that in detailed design. So for each of the attributes, the data type is specified. So zone to price is of type table. Then we have the operations. The signature for the operations is specified. So get zones basically returns an enumeration, and it takes no inputs. There's no inputs needed. Get price takes as input a zone value, and then it returns a price. So that's the signature of the operation. Now instances, when we talk about an instance represents the object that belongs to a class. So that's an object or a phenomenon or a state. So that's the actual real thing that has some values. So all of the attributes in here will have values. When we're talking about class, we're just talking about an overall description, a template of what is expected from objects of that type of class. Now when we talk about an instance, this represents the actual phenomenon or the actual object with data. So in this case we're talking about instance tariff 2006. This is an object, an instance that belongs to the class tariff schedule. Now because it's an instance, it is underlined. So typically instances are also always underlined. They're specified as the instance name colon the class name. And then inside the detailed description, what we have are the attributes and their actual values. So this zone to price, it's a table with the values. So all of the values are indicated in the class diagram for instances. That's what you see over there. Now so like I said, the name of the instance is underlined. Now there could be a situation where the instance name is not known. It's called an anonymous instance, and that's fine. In that case, the name of the instance is left blank, and then we use the colon and the class name, the class to which it belongs, and underline it, indicating that this is an anonymous instance. Now even though it's an anonymous instance, instances always have data, so they have values, so we specify the actual values that are stored in its for its attribute value. So it's important to know the difference between classes and objects, and this is probably if you've done an object-oriented programming course, you'd have seen that there, and you probably already know it, but I want to make sure I reiterate it. A class is basically an abstraction, modeling an entity that's used in the application or solution domains. It's basically an abstract concept, and the idea is to provide a template description of all the attributes and the operations of the objects that belong to that particular class. So examples would be, say, passenger is a class, ticket distributor, server, tariff schedule. All of these are classes. Now when we talk about objects, that's the specific instance of the class. So Joe is a passenger who is purchasing a ticket from the ticket distributor. So Joe is basically an instance of passenger. The tariff for 2016 is one particular instance that has the entire tariff schedule for the year 2016. So it has the actual data. It belongs to the class tariff schedule. Server, again, say server with the ID 101. Server 101 would be an instance of the server class. So server 101 is the one with actual data. So those are some examples of objects. So class versus object, it's important to understand that difference. The next thing is associations. So basically in a class diagram, we first identify all of the classes, and then we want to identify associations between classes, and they're denoted as relationships. So basically it's the edge represents that relationship, and very often we also specify the multiplicity of the association. So that's basically indicating how many objects the particular instance of the class can reference. And we'll talk in more detail about this multiplicity. So say for example, there's we saw this where there's tariff schedule and trip leg, and then there is an association between them, and the multiplicity is specified on the edge. And the multiplicity of tariff schedule on this side is many, and star, basically star indicates many, so the multiplicity of tariff schedule is indicated on trip leg side, and then the multiplicity of trip leg is indicated on the side of tariff schedule. So what this really means is an instance of tariff schedule can be associated with many instances or multiple instances of trip leg. That's what this star on the right hand side means. And then an instance of trip leg can be associated with many instances of tariff schedule. That's what the left hand side multiplicity symbol indicates. Now for many we use a star, but then you could have a specific number like 1, 2 or any specific number. If it's many and unknown, we just mark it as a star. So there's different kinds of associations possible, one-to-one association, a one-to-many association. What we saw in that previous example was a many-to-many association. So let's look at some examples. Let's look at a one-to-one association first. Say there's a class called country, and then the attribute that it has is a name which is of type string. So the name of the country is represented using that name attribute. And then there's a second class called capital city, which also has a name attribute which is of type string. It represents the city name, the capital city name. And then there is an association between these two classes, and it's a one-to-one association. What that means is every country can be associated with and every instance belonging to country can be associated with exactly one instance of capital city. That's in when we're talking about in this direction. And then when we look at it from the other side, from capital city, every instance of capital city can be associated or can belong to exactly one country. So that's in the reverse, in the opposite direction. And that's what so it's basically the multiplicity is 1 on both sides. That's when it's called a one-to-one association. Here's another example where we have the polygon class, and then there's a point class. The point class has attributes x and y, both of them are integers. The polygon class has no attributes, but then it has the operation draw. So that's the behavior of a polygon. Now this is a one-to-many association. Now by default, when nothing is specified, it's treated as a 1. Now what this means is an instance of polygon can have many points, so it can be associated with many point instances. So that's what the star on the right hand side means. The polygon is associated or can reference many point objects. Now on the other side, a point, any instance of point can be associated with exactly one polygon. That's what the 1 on the left hand side means. And like I said, by default, when nothing is specified, it's the association is the multiplicity is 1 by default. So this is a one-to-many association. There's also the many-to-many associations examples. Say we're dealing with a stock exchange and multiple companies registered with stock exchanges. So the left hand side, so the multiplicity is star on both sides, which means it's a many-to-many association. So now each company has a ticker symbol to indicate to uniquely identify itself. So what this many-to-many association means is that each instance of stock exchange can be associated with or can refer many company many companies. So a stock exchange can have many companies registered with it, and then each instance of company can be associated with multiple stock exchanges. That's what the many on this side means, which means a company can be registered with multiple stock exchanges at the same time using that same ticker symbol. So that's what that many to many association means. Next, we'll discuss the term model-driven software development. The idea is, what we're doing here is we have the requirements from our client or the client expectations. We understand those requirements, analyze those requirements, and then once the requirements are finalized, we come up with a model. And then once we have the model, then the software is developed based on that model. And this process is basically called a model-driven software development. So we start with the reality, and say if you're dealing with a stock exchange example, a stock exchange lists many companies. Each company is identified by a ticker symbol. So that's the information that we have, and now we need to model the software to handle this, to handle these operations. We conduct an analysis, and the analysis results in what's called an analysis object model. So we need to come up with a class diagram, a model for it. So the key objects in this case are the stock exchange and company. We know that the company has it's identified by a ticker symbol, so we put that in. And we know that a stock exchange lists many companies, so lists is the association between them, and it lists many companies, so the associativity is many on the company side. And then each company can be registered with multiple stock exchanges, so we have the many on the stock exchange side as well. So what we ended up with is a many to many association. So that's our initial object model, a high level object model that came out of the requirements analysis phase. And then once we have the model, what model driven development means is basically then we take this model and convert it into source code. So that's the implementation part. And then there's a number of tools that help with this conversion or automate this process. They're able to take a model and convert it into source code with the stubs. It's like a template source code where the skeleton is laid out for us, and then some of the detailed logic and implementation needs to be provided. So basically, this model translates into two classes. There's one class called stock exchange, and this is Java code. So in Java, this is how it would look. We have two classes, one for stock exchange and one for company. Now the company has an attribute ticker symbol, so there's a variable called ticker symbol. And then every association, an association means that stock exchange refers to company, or it maintains a list of companies. So here's a vector, an attribute of type vector to hold the list of those companies. And then similarly on the other side, on the company side, because it references stock exchange, it also there's another vector type attribute to hold the list of all the stock exchanges that this company is registered with. So you see that it's fairly straightforward to automate this process, because each class in here basically gets converted into a Java class. All of the attributes become the variables, and then the data type, if the data type is indicated, then the data type can be used in that skeleton code. It can be specified, and then all of the associations also get converted into an attribute in the class. So it's fairly straightforward that way. So that's how we go from a problem statement to code. We started with this problem statement, we came up with this model, and then we're able to get to code from there based on that model. So because we have a stock exchange class here that gets converted into the Java public class stock exchange, and then similarly for company we have this second class, because there's the ticker symbol attribute that corresponds to the class attribute there, and then because we have the many association from company to stock exchange, there's going to be an additional attribute which is, it needs to be some kind of a list attribute, a list, a vector to hold multiple values because it's a many association. So there we end up using vector, a generic data type, and then that can be changed later on, but this is the kind of skeleton code that's provided by the tools. And then because there is a many association on this side as well, we introduce another attribute inside stock exchange to hold the list of companies, and again it's of data type vector to hold many companies, ticker symbols. So it's important to remember that all of the associations are also mapped to attributes. So those were generic relationships. The relationships that we saw so far, the associations, is a generic association, and then a description of that relationship can be provided using a label by labeling the edge, and then we also specify the multiplicity of the association. Now there could be other types of relationships. Aggregation is one of them. It's a special case of association, and it specifically denotes consists of hierarchy. The idea is to do some kind of an aggregation. So to provide you with an example, say an exhaust system. Class exhaust system could be an aggregate that comprises of a muffler, it comprises of a tailpipe, and maybe there could be other components. So in this case, the association is more specific, and it's indicated as this consists of hierarchy, and in UML class diagram notation, it's the association with this diamond symbol indicates that aggregation. And then in terms of multiplicity, on the subcomponent side, the smaller part side, we specify a number. So basically an exhaust system, an instance of an exhaust system consists of exactly one instance of muffler, and it consists of a range 0 to 2 instances of tailpipe. That's what it means. So now here our multiplicity also has a specific meaning, and it's related to the aggregation basically. So it's here the idea is to represent this consists of hierarchy. The aggregate is the parent class. So this is the parent class, which is the aggregate, and these child classes are the components of the aggregate. This can be further specialized with a composition association. So a composition is a stronger form of aggregation, and it's denoted using the solid diamond symbol. So what this means is that when composition is used, like over here, this is composition. What it means is that the smaller parts, the child components, they don't exist on their own. It doesn't make sense, their existence doesn't make sense without the aggregate or the parent. So the whole or the parent or the aggregate controls the parts, and it destroys the parts when it doesn't. If the ticket machine doesn't exist, then the zone buttons don't make any sense. So zone buttons are destroyed, they don't exist on their own. But then a ticket machine is an aggregate of 3 zone buttons. It has 3 zone buttons in it. But then the association is a composition, which is a stronger form of aggregation. So zone buttons cannot exist on their own. That's what it means. Another type of association is inheritance. Now aggregation was this consists of hierarchy. Inheritance is it's kind of hierarchy. It's a special case. Again, this is another special case of our generic association. The idea is to introduce some kind of a taxonomy. So an example would be, say you have button, which is a more generic class, and then we have different types of buttons or different kinds of buttons. Cancel button is one kind, a zone button is another kind. So these are more specific classes. So here we are specifying a taxonomy, and this is indicated using the triangle symbol. indicating inheritance. So class cancel button is a specialization of button, zone button is a specialization of button. So that's the reason it's indicated using this inheritance relationship. Now also the child classes, they inherit all of the attributes of the parent class, all the attributes and the operations of the parent class. So what that means is, when we are providing detailed design for the child classes, we don't have to repeat the attributes that are already there in the parent class. It's only the specialized attributes, or the more specific new attributes and new operations is all that needs to be specified. Everything else that's there in button is automatically inherited in cancel and zone button. Packages are also used in UML models. They basically, the purpose is to increase readability and organize. When there are multiple classes and if there's a number of them, it's a way to organize them for better readability into subsystems basically. So say if we are creating a model for a banking system and there's different kinds of classes. So this first one, all the classes related to account are in this first package called account. All of the classes related to customer are in a customer subsystem, and then there's a bank subsystem. So there can be multiple subsystems into which these classes are organized. So that's packaging, and basically the notation is to use some kind of a system boundary and a classifier to indicate the package name. So the next thing I want to talk about is a process and how object modeling is done in practice, and how you should be doing it when you start doing the modeling from scratch. The first step should always be class identification. Think of the broad classes and always start at the high level classes. What are the key high level classes, and then think about further detailed classes. So class identification is the first key step, where you think of the name of the class, the attributes and the methods. And then very often the first names that we come up with for the classes and the attributes may not be the best. So it is an iterative process. So we always think about and rethink about some of the names that we've chosen, and is it representing our concept accurately. So say for example, we come up with a class called foo, and then we say that there's attributes amount and customer ID, and operations deposit, withdraw and get balance. Now what is this concept really, and what is the purpose of this concept? What are the kind of objects that belong to this particular class? And then you rethink and make sure that the name that you have correctly represents it, and then come up with that correct accurate name through a brainstorming process. And that's where teams are involved with multiple people, and all of them brainstorming to make sure that the modeling is being done correctly, and the concepts are being represented accurately. So say we come up with this class called account. Say it's a banking application, and we're dealing with different kinds of bank accounts. So we come up with this class called account. So far we have two attributes, amount and customer ID, and then operations, deposit, withdraw and get balance. Now also we need to think about, do we have the correct attribute names? Do they represent the attributes correctly? Are the operation names correct, and do they represent the operation correctly? So that's also a part of that brainstorming process. Now here we said customer ID, but does that accurately identify the attribute? What is the purpose of this attribute? Is it identifying the account, or is it identifying the customer who's using the account? And based on that we come up with the correct attribute name. In this case we are interested in information about the account, so we need a way to identify the account, so that attribute should be named account ID. Then there's an amount, that's the balance amount in the account, so that's indicated using the amount attribute. And then these are the three high level functions that this particular object has: deposit, withdraw and get balance. So that's again a high level design. Now we're not thinking of more detailed, there could be other methods that are needed, but then that can be thought of in a more detailed design. So our first step is find these new classes. what other classes are needed. So then we come up with, say, customer. There's a customer because it's the customer who owns an account. The customer has a name, and then the customer also needs a unique identifier. Now we make sure we name those IDs correctly. So in this case we call it a customer ID and a name. And then there's a third class that we need, which is called bank, and then the bank has a name. Now we want to make sure we continuously again in an iterative way review those names, attributes and methods of all of the classes that we've identified so far. Again, there's a name in customer and there's a name in bank. There are two different attributes. The name over here represents the customer name and the name over here represents the bank name. Again, as part of this modeling process, one might want to be more specific and clear and indicate that this is the customer name, so call it a customer name, and this is the bank name, and so call it the bank name attribute. Then our next step is to find associations between classes. So account is associated with the customer, and account is also associated with the bank. So those are those generic associations. Then we need to also think about labeling those generic associations. What does that association mean? So a customer owns an account, so we provide that label, and then a bank has accounts, so we've labeled our associations on both ends. Then we need to determine the multiplicity of the associations. So an instance of bank can have how many accounts, an instance of customer can own how many accounts, and then we need to look at it from both sides. An instance of account is owned by how many customers. An instance of account is part of how many banks. So that's what we need to think about when we're thinking about multiplicity. So a customer can own multiple accounts. So we place the star on the account side of the association. And then an account can have a maximum of 2 customers. So if it's a joint account, a maximum of 2 customers. So we mark the multiplicity as 2 on the customer side. Similarly, a bank can have multiple accounts, so that's the reason for the star next to the account. And then an account can be contained or is part of exactly one bank. That's the reason we're leaving it as the default on the bank side, or you can mark it explicitly as 1. Whether you mark it or not, by default it is 1. So it's a one-to-many association. The next step is to review those associations. Do we have the correct associations? Do we have the correct multiplicity? So we review them. As part of this reviewing, maybe we realize that a generic has association between bank and account is not the most, does not represent it correctly. Can we do better? Can we be more specific about this association? A bank is basically an aggregate. It comprises of multiple accounts, so why not use the aggregate association? So that's indicated using the diamond symbol. Then we further review it and think about is it aggregate or is it composition, which is a more stronger form of aggregation, because can an account exist by itself? Does it make sense for an account to exist by itself? It relies on bank and it can exist only if bank exists. So in that case, a composition association makes most sense. So we basically change that to the composition association. So so that's how we begin to put the different objects together and the associations together. Then we think of taxonomies and find if there are any taxonomies in there. So account, there could be different types of accounts. We can have a savings account, a checking account, a mortgage account. So basically we indicate that using the inheritance association. So this is a special kind of one. It's the kind of. Savings account is a kind of account. Checking account is a kind of account. They're more specialized accounts. So as you can see, we don't have to repeat any of the attributes or operations of account. They're all inherited automatically by the child classes. The only thing that we need is any specialized attributes or operations. So withdraw is going to be different for savings, checking and mortgage. So they'll need their own implementation of withdraw operation. So that's the reason withdraw is listed in there. So basically, in order to simplify and organize the models better, it's okay to split up the diagrams into multiple parts. So if you want, the taxonomy can be separated out as a separate model from the remaining class diagram. So it's okay to do that. And normally it's done when the diagram gets too cluttered and too huge, just to make it for better readability. It can be separated out into multiple, and taxonomies specifically can be shown separately. So that covered all of the class diagram notation that's available. So basically how we indicate our classes, attributes, operations, how we indicate instances using the underline, and then we specify associations between classes, we specify multiplicity between for each of the associations, and then for generic associations we just label the association to describe it. There can be more specific associations like an aggregation, composition, which are basically the consists of a hierarchy, and then there could be inheritance type of associations, which is more of the kind of hierarchy to show a taxonomy. So these are some of the different graphical notation that's available with class diagrams to indicate all of our objects based on object-oriented methodologies. Now let's do a quick exercise, which is basically drawing a class diagram for a simple watch. Now this simple watch is basically has an LCD display to indicate the time in hours, say minutes and seconds, like that, and then it has, say, 2 push buttons, 1 and 2, that can be used to set the time or change the time, and then so basically all it has is these push buttons for the time, to set the time, the LCD display to view the time, it has a battery, and then the watch shows time. So that's really the purpose. So that's what's provided to us as a specification, as requirements. Now based on that, if you need to come up with a class diagram, the idea is, again, you use the process that I just walked you through. Identify the classes first, followed by their attributes and operations, followed by associations between the classes, and then followed by the multiplicity. So we basically go through that process. In this case, the different possible classes would be, say, the LCD display, the battery, then there are the buttons, and then the current time that's being displayed. So those could be some of broadly the classes, and then you further need to think about the attributes, operations, and how they're interacting with each other. So let's look at the class diagram. So the simple watch, we can have a class called simple watch, which is an aggregate that's made up of, say, push buttons, so there can be an association there. Each simple watch has, say, 2 push buttons, then so that there's our multiplicity. Each push button belongs to a simple class, and this can be represented using the aggregation like that. In addition to that, we have classes display, battery, and time. So simple watch comprises of all of these. Now it's up to us. We have to think and see if we want it to be an aggregation or just a generic association. And then as you can see, the multiplicity is being specified. Each simple watch has exactly 1 display. Each display belongs to exactly 1 simple watch. Each simple watch has exactly 1 battery, and each battery so each simple watch instance has exactly 1 battery, and each instance of battery is associated with one simple watch, and then the same thing with the time class. So as you can see, we've identified all of the classes, the associations between the classes, and the multiplicity. We can further, the push buttons can be further, taxonomy can be created. You can have a generic button and then different types of button, if there's two buttons, then one is to set the time and the other one is to change the time. So we can get into those details in the detailed design phase. We first always start with a high level design, wherein you identify the high level classes and the associations, and then iteratively get into further details. So the next step would be also to think about what are the different attributes and operations and indicate them for each of the classes, and then go through this brainstorming process and iteratively further refine the diagram. That's the process that's followed for class diagrams. So that covered all of the notation that we would need for class diagrams. In follow-on videos, we'll look at other kind of UML diagrams that focus on modeling the dynamic behavior of a system. Okay, thank you.